Well, thank you, Cyril. Thank you, everyone, for coming. Just for the record, those are all University of Montreal, different parts of it. So I'm going to be talking about how to make analysis reproducible. And when you do an analysis, essentially you collect data, and that I'm not going to cover. You have your raw data, and you're going to have to apply a series of tools to transform this data and turn it into a finding that you think is valuable for science. And so typically you have to apply a series of tools, sometimes sequentially, sometimes in parallel. And if you want to reproduce that, well, in short, you want to make sure you can find your data again in the future, that you can find the tools you've used again in the future. And if you've automated the application of all those tools, it's going to be very easy to reproduce what you've done. So this is kind of like the general idea, and so it sounds really, really simple. In practice, I'm super happy I can have like one of those, inspirational quote, the cheesy things you get in your email by maybe your cousin or something. There is no one giant step that does it. No. It is a series of little steps, and I think that really applies at reproducibility of analysis. I don't think there's like a recipe that's going to make you actually able to reproduce your analysis in the next 100 years. Actually, some people are skeptical, that maybe in 10 years or in 15 years, we're still going to be able to run the same kind of software and library we use today. So maybe we need to come to accept simply that we will not be able to reproduce in the long term. I don't know about that, but what I know is that there's a lot of little things you can do to make what you do more reproducible. Maybe within your lab, maybe within the next 6 months, but every time you take one of those little steps, in effect, you're going to probably simplify your life in the future. I think that's something that needs to really be clear, that the reproducibility, the first person you're helping is yourself and the people in your lab. Because in 6 months, if you want to retry something or be sure of what you have done in your experiment, or if your students need to communicate and pass project, having reproducible workflows is going to help tremendously with that. So it's at the end of the day making better science one step at a time. So if you want to automate things, the first thing to do essentially is to learn to code. I mean, you can automate analysis without coding, but coding is the most versatile, most efficient, most well-documented way of doing it. So here you have a picture of former US President Obama cheering young students to do it. I think if people from high school can do it, university students should be able to do it, even if they're registered in non-computational field like psychology or what have you. Also, what I like about that picture is that I can see President Obama as a US president, and somehow that makes me happy. Don't know why. So in terms of programming languages, there's a lot. And I think, there's lots of resources online. I don't necessarily need to comment and tell you, what the best language is. But I wanted to have this slide because I feel that there's a bit in the community this idea that there may be one language that's good for reproducible science and that the other one would not be good. I do not like this attitude. I think it's not productive. And that you can advance the reproducibility of your science with a variety of different languages. Now, having said that, probably if I were to recommend one to learn, that would be Python. And the reason why I do that recommendation is because it's very widely used and it's also very versatile. You can really do lots of different tasks with Python. And for the students today, like learning a new language in terms of their employability in the future, it's really a big plus. Now, in our community, I think it's still the most widely used is MATLAB. And one of the advantages of that language is that you have a lot of good packages and that have been historically dominant on the scene there, and you can absolutely work without doing reproducible analysis and open science, especially since you have an open source clone of MATLAB, which is called Octave. And finally, lots of people like to use R because it's extremely powerful in terms of its statistical packages. So just like a quick overview. So learn one, and when you learn one, then it's becoming very easy to learn others because it's like natural languages. So it's and actually probably not such a big deal which one you pick. They resemble each other. There are lots of great resources to do that. I've put a link to the software carpentry. They have online tutorials. They also organize workshops, so you can, like, in a city nearby you or in your own city, attend workshops that are really well run and with instructors that are well trained. There's this mailing links called NeuroStars. If you have questions on neuroimaging and software development, you can get help there. And finally, there's also a series of hackathon called Brain Hack, and the hackathon of OHBM sort of modeled after that. So that way you can meet people doing software development and neuroimaging and improve your skills through getting involved in projects. Now, if you start coding, that's like really a first step towards making things more reproducible. But it's not the end of the road. As I said, it's lots of little steps. So what typically happens when you have a paper is that the paper is really nice and clean. You have a number of analyses, very straightforward results, very convincing. Now you also have all those things you tried, and that is very well described in your supplementary material. So you have a pretty good picture. But what actually is happening is that there's all those things that are on your hard drive, all those like failed iterations, things you actually even forgot about, and that are definitely not listed in the supplementary material. Deep inside that mess, here there's a monster with one red eye. That's the code. It's probably saved with like weird file names, and you yourself in 1 month will not be able to know exactly what script you've used. I'm caricaturing a little bit, but I think I would describe my own practice like 10 years ago fairly accurately with that drawing. So, you know, the idea is to make sure that because the code plays such a huge role in your analysis, to make it a first-class citizen, and taking it back from here and maybe like bringing it up there, and like, you know, tidying him up a bit. So the way to do that is actually to control the versions of your code. And to do that, we have fantastic tools, because it's a problem that's pervasive in all the industry. Code is used to run the world. And so we have really great tools to maintain great code. So it's pretty easy. So the general idea is that instead of having one file that you're going to change and maybe save some version by just renaming, you're going to use a tool that's dedicated to tracking all the changes you're making to your code. So in a sense, what you have is what's called a revision history. You have a series of states, and between each state, you're going to have a description of what's changed to your code. And the tools you can use to keep your revision history, they're smart. So if you have a bunch of different files, every time all they're going to do is like store the differences to the files that have changed, and in an efficient manner. So it's a bit like the time machine on a Mac computer. You know, you can go back in time, except that here you don't really have limitations in like how back you can go, because it's really very efficient the way it's stored. So you're going to decide, like, you know, today I made some progress. Oh, I'm saving a state. I'm going to go for coffee, come back, work a little bit more, save another state. And every time you can document sort of an overview of why you made those changes, so you can get a real history along your projects of all your code. So if you decide to embark on learning that, there's this platform called GitHub. It's a website. It makes it very easy to get started. It provides some pretty nice user interface. And there's some tools, for example, here. So on the left, I have a it's a script. I've changed it, and it's going to highlight for me all the changes I've made. So on the left, it's the old version, the right, the new version. I can see I've added a couple lines here, and I've removed a line there. So it makes it very easy to know what you've done between today and 6 months if your results have changed. You can really track down what lines have changed automatically without really thinking too much about it. There are tons of really good resources to learn GitHub. We had a tutorial this morning led by Greg Kia. He's here. Thanks, Greg. There is a 15 minutes introduction video made by GitHub. I've put the link here. There's also what's called a no-sum list. It's like a resource on the web that's actually on GitHub, so people can propose to change it in a community-driven way. So you're going to get lots of really good resources to learn Git from the basics, but also to refine your Git skills and take them in the next level if you're already using Git. So you code and you now control the versions of your script. That's good. But you also need to control the versions of what your scripts use. If your script is based on SPM, what SPM? If you check out the logos of SPM, you can see SPM's versions are widely different. It's, sometimes they're just flipped, but generally they go for completely different styles. That's what they do with their logo. And you can see that. So just imagine what's happening in the code base, everything. Not much. So just you get those versions of SPM. Just for SPM 8, you get 9 minor updates. So really you have SPM 8.1, .2, .3, and so on and so forth. So ideally, not much is happening, and really, if you change the versions of SPM, it will not change your results. I don't think that's the case. I mean, yeah, it depends what you do, really. I've linked to that paper here, Malone and colleagues, that just compared brain volume in SPM 8 and SPM 12. Oh yeah, segmentation change. So registration change, those very much impact everything you do in the software. I'm not using SPM a lot, so I cannot comment extensively. With the software I use a lot based on the Ming tools, I can tell you things change. Things change. It's actually very interesting to know by how much they change, what steps change. But interestingly, in our community, we don't document that. And we need to wait for other groups to actually make papers to know if there are changes between SPM versions. The SPM developers themselves do not provide really metrics when there are new versions to know what's changing. So Tristan Glattard is in Montreal. He's a fantastic guy. Unfortunately, he's not here during the conference. But he got this paper out a couple of years back where he tried to simply run the same analysis in FSL and the same system, and just changing like very minor libraries in the system. So nothing in FSL changed. What changed was the libraries that were depending on in their base system. And so they ran some IC analysis, and I'm not going to get into the details of like what those numbers are, but basically they've shown that even like very tiny differences in the OS can still cause some measurable differences in your outputs in an FSL IC analysis. So there's this idea that because it's a computer, it's going to give the same answer. It's just no. There are some differences. How severe are they, and how much they could impact your conclusions? I think we actually need to have a lot more science to tell us about that. But the fact that this is an issue is beyond any doubt. So if you control the version of your script and the version of, say, SPM, it's already great. Maybe in your paper you could consider, citing which versions of SPM you've used. If you are curious and you really want to become a bit paranoid, there are tools out there that are really more for the geeks, but that are not actually that complicated to manipulate. So basically, there's two big families. The first, like the older one, are virtual machines. So virtual machine is pretty much like playing a machine inside your own machine. So say you have a Mac computer and you're going to play a Windows operating system, simulate the Windows operating system inside your Mac system. So maybe you're going to do updates to your computer because you want to apply security patches because you're a responsible person, but you're going to run your software analysis inside a virtual machine which will not change. So also the virtual machine, you can install it on different computers. So you don't depend anymore on your particular setup to be able to reproduce your analysis in the future. I have a friend, Julien Cohen-Haddad, like he never updates his operating system. He tries to keep his laptop as long as possible, just that he can reproduce his computation. It's like having a virtual machine is much more convenient than just like keeping your computer for 10 years. The other, like maybe slightly more modern option are like containers. Containers work on a completely different technology than virtual machines, but I'd say from a user perspective, they deliver essentially the same benefits. Like they're more reproducible, but they're much faster. They're typically smaller, and they're also running something in a container is almost as fast as running it on your normal computer. Well, when your computer has to simulate Windows in order for you to be able to run the software that's of interest for you, it's using a lot of your resources. So virtual machines tend to be a bit big and slow, and containers to be more lean and fast. But those are two alternatives. And now there's a lot of software you will find that you can actually download and install in Docker container. So software developed in my lab is shipped like that. I know Chris has been recently piloting an initiative called the BIDS apps, which are a series of software for neuroimaging, and they all come as container. So I'd say it's starting to become really, really easy to access and use those technology, even if you're not a hardcore geek. Whatever. So, taking it a step further, if you control the version of your own script, of the library you're using, you've put everything in a container so you're able to reproduce it at will on any machine. Maybe you want to also share those scripts you've created with the world. And for that, there's lots of platforms which lets you do that. I'm just citing Zenodo is one. It's run by the CERN. Switzerland, they have lots of money and big computers. So they figured we may as well offer the community to use some of our storage because anyway it's a drop in the bucket for us. So as far as like we're concerned in 2017, I think they don't really put limits on the amount of data you can put on there. I think 500 gigabytes would be okay for them. And it's really super easy. One of the benefits, you can get a DOI, that means like a digital object identifier. It's a unique number that can be used to link to your data for the foreseeable future. Actually, typically papers are associated with DOI, but today a lot of other objects are associated with DOI, including dataset. So dataset can be code. So if you have your script, you just put them all on Zenodo. They're going to have a unique identifier, and they will be accessible for the foreseeable future or until the CERN initiative closes. When you do that, you really want to consider licensing your work. So licensing, it sounds like something very legal, very complicated. It's not. Licensing, you use the MIT license. It's 2 paragraphs of text, and that says, take my things, do whatever you want with it. Sell it, modify it, copy it, reuse it. Just don't come and complain it doesn't work. I don't want a lawsuit. So I would say that if you need to know just one thing about licensing, that's enough. There are different licenses with different benefits. But as a first go-to option, I'd say MIT or BSD are equivalent. They're very short, very simple, and they press basically no restriction except protecting you a little. In terms of sharing your code, what I found useful is to make a little document to describe the different scripts that are associated with the paper. So that's a paper we published like 2 years ago. 2 years ago. And when I finalized the manuscript, I went through all my code and I selected the scripts that were critical for parts of the paper. And I just did a small text file on the GitHub interface. And so people who come see my script have just a simple way of seeing which scripts are associated with what, and so they can see which parameters I've used, things like that. You can also try to run your code into something that's called a notebook. A notebook, it's web-based, and that lets you have code you execute, and the results of the code lives just under. For those who are familiar with MATLAB, there's something that's called like the publish option. In MATLAB, when you have a script, you can press publish. It's going to create a document that looks like that. The Jupyter initiative, it's like you're editing directly the document. It looks good, and it's also interactive. And the beauty of that project is that it works really with everything. It used to be for Python, but it works well with R, and today it also works with Octave, which is essentially MATLAB, so that's MATLAB code. So when you work with with this type of interface, it's very, very easy to share that with a colleague, because you'll see immediately all the code, all the results. I just wanted to give a plug to like two services, online services. So Binder is a service that hosts those type of notebooks, and they make them reproducible for you. Like you can give them a Docker container. It's going to run the notebook inside the container for you, and also make the notebook interactive for anyone. So if you've done a code, you like it, it's a part of your paper, you can put it on Binder, and anyone can just come and re-execute your code, change it, see what it does. So it's a pretty fantastic initiative. It's still like a bit of, new, but very promising. And there's also the Open Science Framework, which is offering lots of services for you to basically centralize all the things I mentioned. So you have a bunch of notebooks, maybe you have code on GitHub, you can have everything linked into a central place, nicely managed, and that you can make public at the end. So the whole collection of all those things you've done to make your project reproducible appears in a single environment. So maybe that's the future of reproducible science. I think it is. So it's definitely worth checking out. So just last part of my talk is that once you everything I described really works well when you have a pretty simple analysis to run. Okay, so if you can just make a script that's like 100 of lines or 200 of lines, and it's going to run in maybe 10 minutes, you're really good to go, essentially. If it's in a notebook, you can share the notebook. Well, you don't need anything more complex than that. But if you're processing, like, say, the UK Biobank data set, and you have, 10,000 subjects, and your analyses are going to take, like 2 weeks to run, or like 2 years, really, if it's resurfer, then you need to other technology, essentially. You need to move on from just having a script. So then you really need to compose what's called a workflow or a pipeline. So you are going to have to apply a series of steps. And instead of doing every of those steps yourself or in a big script, you want to take the time of describing formally, I want to do tool 1, then plug the output of tool 1 in tool number 2, and so on and so forth. So describe in advance everything you want to do in a formal way. And then once you have that, you're going to ask to what's called like a pipeline or workflow execution engine to execute it. So if you have several subjects that can be processed in parallel, the workflow engine is going to detect that and run them in parallel. So one of the benefits of using this type of technology is that it's scalable. You can really, if you have lots of computers, you can divide your computation time by the number of computers, provided you have enough subjects. And another benefit is that you can share the description of your workflow. That workflow becomes an object, just like this little diagram is kind of a schematic of the workflow, but really you can produce this type of diagram from your workflow. So it becomes very easy for people to review what you've done, the type of parameters you've used. It's much simpler than if you actually share a long, complicated script. So there's lots of options out there if you want to compose pipeline, just plugs on some projects. The NiPipe project is Python-based, and it's sort of like a monk effort in the sense that they've painstakingly assembled interfaces to all the major neuroimaging software. So when you use NiPipe, you can really mix like FSL, SPM, AFNI, all that in complicated pipelines. They also have existing prepared workflows ready to go. Another system for MATLAB is automatic analysis, which offers the same kind of services but more geared towards SPM and EEG lab. And finally, I'm developing something that's called the PSOM, and it's also a pipeline system for MATLAB and Octave, and it's more like a general purpose. It doesn't have interfaces with existing software, but what's cool about it is that it's really fast. If you have really big computers, you can take advantage of them with that. There are also like online systems that exist that are going to offer standardized pipelines. So Loni have been around for a while, developed by the Toga lab. So you can really implement workflows through the web with them. CBrain is another platform that's developed in Canada by Alan Evans' lab, where they try to offer a few highly standardized pipelines, such as the 3Surfer surface extraction tool or the CVET surface extraction tool. So they don't have necessarily very flexible pipeline, but they are very good pipelines. And a lot of computers to make things fast. And finally, I mentioned already the BIDS apps initiative from Chris, which at this stage just a bunch of containers you have to install. But soon, I think they're going to also have a portal that you can run those containers online. So it's super exciting. Actually, I think the BIDS apps are also going to be, you're going to be able to play them through CBrain. So, you know, it's going every direction, reproducible science everywhere. So, conclusions, small steps. You don't have to do them all, but learning how to code, controlling the version of your code, try to control your environment, share your code, or use pipeline systems are all types of new skills you can learn that are going to help you and help science be better. Just a little reference to a review written by Chris and Russ Poldrack recently that discussed the same type of topic I've covered here. I also wanted to apologize because there's lots of tools that I've not listed here, but I've already listed probably too much. But in the Open Science Room, we have like about 20 demos running all of OHBM. Most of these tools are useful for reproducible science. So check out, it's in the official program. You have a list. And feel free to drop by the Open Science Room. It's just right down there at the corridor. And so if you want to meet me, Chris, or other developers of those tools, Cameron in the background, just drop by at the Open Science Room and it will be our pleasure to talk.
All right, thank you, Pierre.